I'm sure.
So we differentiated this fraction, also called a quotient. So you can differentiate using the quotient rule or the fraction rule, but it's really just the product rule in disguise.
Yeah.
So we did that, and then we've got this. Let's do that. So differentiate log of 1 over x squared plus 9. Thing is, right. Log of 1 over something can always be rewritten how? Where was it we were discussing this? It wasn't there. Okay, it was on a previous panel. But the thing is, well, for example, given that logs are powers, a negative log, a negative power, is the power you have to raise something to get 1 over.
Right. Okay.
And this is asking. So when you look at the log of 1 over something, you're talking about a power necessary to raise e to get 1 over. Well, it's going to be a negative power, isn't it? So this is the relationship. We could just treat it like this. Because log of 1 over anything equals minus log of the thing.
Right, okay.
It might be worth finding. It was recent. Let's find it. Well, let's see if it's on this one anyway.
Yeah.
View 50%, say. Whoa. I mean, there was some integrating to a log. Nah. Oh dear. We lost some there. Did I forget to save? Anyway, so on that basis, we could just say, okay, differentiating this is like differentiating the minus version.
Yeah, minus log x squared plus 9. Oh yeah, you wrote it.
And how should we do that?
So we're differentiating.
Yep.
Okay. Well, so should we? Okay. Well, if we split it, ln minus ln, and then x squared plus 9.
When you say split it, do you mean as a product?
No.
Good, because it's not, is it?
No, yeah.
Of something like sine of something. It's not sine times the thing, is it?
Yeah, no. It's just I'm saying make the blob x squared plus 9.
Good.
Yeah.
Absolutely.
And then you're going to get ln differentiates to 1 minus 1 over x.
Yes. Negative ln will be minus 1 over. Oh, no, sorry. Did I mishear you? What did you say?
Well, ln differentiates to 1 over x, doesn't it?
1 over anything, yes.
Yeah.
Oh, sorry, that's irrelevant there, but yes, you mean 1 over thing, yes. So
we'll get
Ln differentiates to 1 over blob, so
we'll get 1 over x squared plus 9
yes,
minus 1 over x squared plus 9.
good.
And then we'll get times 2x.
Yeah. So we could simplify very slightly by just
saying minus 2x over x squared plus 9. Yeah.
Yeah, quite good. Good. Right. So that was relatively simple. Whereas if we tried to do it as a chain rule, I think we could still handle that. Let's do it as a chain rule instead of using that switch from log to minus log. What kind of chain rule could we have here? I mean, what kind of inner function, what blob could we have instead?
One over x squared plus 9.
Yeah, which is fine. And then we'd have a further blob inside, really, wouldn't we? So we'd expect
the inside blob would be x squared plus 9. Yeah.
So that's inside that, which is inside that. But that's okay. We found that it's okay to deal with sort of several inner functions. They'll just come out in turn. So let's say, okay, firstly, Lin becomes what?
Lin becomes 1 over.
1 over. Same stuff.
And then you've got, well, the fact that it's 1 over something just means that it would flip over.
Yes, indeed. Indeed it does. So we'll do that in a minute, but what, should we do it now? Are we done, basically?
So then we'd get 1 over x squared plus 9, wouldn't we?
I mean, actually, when this simplifies, it's going to be simpler than that. What's 1 over something? For example, 1 over a half is?
1 divided by a half is 2.
Yes, because it's like 1 times the reciprocal of a half. 1 times 2, which is 2. In general, 1 over x is?
1 over x is x over 1. X.
X, yeah. So this is actually going to be just x squared plus 9.
Yeah.
Right? But it's not the end of the story, is it? Because we need to apply the chain rule. I mean, log of blob is 1 over blob, yeah.
Yeah, and then we're going to say, so it would be times.
Yeah.
Times.
Yeah. 1 over wasn't the most friendly way to write this. I think I'm going to suggest writing it as log of, 1 over, but we could write what instead of 1 over?
To the minus 1.
Minus 1. So if we think of it as blob to the power of minus 1 inside, so yes, we've got 1 over this to the power of minus 1. But now we want to multiply by the inner function is going to be, what's the derivative of blob to the minus 1?
The derivative of blob to the minus 1 would be minus 1 blob minus blob to the minus 2.
Exactly. Now are we done?
No, and then times 2x.
times 2x, which is the function inside that, the derivative inside that as well. Yeah, derivative of the function further in. Yeah.
So do you think that will give us the same answer as minus 2x over x squared plus 9?
We hope so. Let's find out. Yeah, let's find out.
We could put minus x squared plus 9 to the minus 2 over x squared plus 9 to the minus 1.
We could. But, you know, I rewrote this as 1 over 1 over.
Yeah.
So I rewrote this in place of that, in place of 1 over 1 over. And we agreed that 1 over 1 over, what happens to 1 over 1 over?
It just cancels the ones.
It cancels because they are what we call self-inverse. They can't, you know, it's a function that is the inverse of itself, so it cancels out if you do it twice. 1 over 1 over is nothing at all. So really what we've got here is what?
It's just x squared plus 9.
Exactly. So rather than putting this over that with the minus 1 there, it might be simpler to say, well, okay, power of minus 2 means 1 over the square, doesn't it?
Yep.
So really what we've got is
x squared plus 9 over minus x squared plus 9 squared, all squared, yeah.
Times 2x. Now, this is good news, isn't it? What can we do with the fraction there?
We could say 1 over minus x squared plus 9, can't we?
Yes, that's right. It's like, you know, that's something times itself, and one of the selves is going to cancel with the top. Yeah, that's what you're saying.
Yeah. Yeah, right. We could just say 1 over
x squared. Yeah, what you said.
Yeah.
1 over.
Yeah.
So it's 1 over the negative of that. Well, the negative in a fraction can go in bottom or top, can't it? Or at the front, even. But let's put it on top on this occasion. So we're just going to have minus 1 over x squared plus 9 times 2x. The 2x could go and sit on top as well, couldn't it?
Yeah, so minus 2x over x squared plus 9.
And so we have got what we had before. Exactly the same result. It was probably easier to do it this way because we just had one application of the chain rule. Whereas here we had an inner function of the inner function and probably a bit more simplifying. Right. Okay. So that's that. And now, oh yeah. Next one. Right. Given the function given, just using f of x as a label for that function, which is a fraction, given that it's increasing on such and such an interval. Now, do you see what we were talking about? Increasing and decreasing, weren't we? Meaning what? What can you say about a curve if it's increasing?
It's getting steeper.
Not necessarily going steeper. It might be leveling out, but this one is still increasing.
So the y value is getting bigger.
Yeah. The reason I'm bothering, you know, to linger on that point is because it's a a one-to-one function will be either increasing or decreasing all the way. We were saying,
Yeah.
weren't we? If it increases and then decreases, then it's not one-to-one, so it won't have an inverse.
Right. Okay.
But increasing just means that the gradient is, what can we say about the gradient all the way if it's increasing? If the curve is increasing, if the y values are increasing, what can we say about the gradient all the way, even though the gradient is changing?
That the gradient is. Sorry, say that one time. What can we say about the what?
The y values are increasing all the time, right?
Yeah.
The y values, how high we are. What can we say about the gradient, which is going to be changing all the time? I mean, the gradient of that tangent won't be the same as the gradient of another tangent somewhere else. There'll be different tangents, but they will all be what?
Positive.
Yeah, positive. Yeah. Sorry, if that was bordering on the obvious.
No.
But it's, you know, it's important to see why they're saying these things.
Yeah.
And on the interval minus k, where do we find this interval on the graph? What part of the graph is that referring to?
Minus kk. I'm not sure.
Those will be points on the x-axis. So what we're saying is that between x values of k and minus k, presumably the y-axis is dead halfway. We can presume that, can't we? You know, in that interval, it's an increasing function. It might come down later on.
Okay.
But what they're saying is between this x value and this x value, the gradient is therefore
Positive.
Positive. And that's how we're going to do it. You know, that's key, really, isn't it? If by interpreting the information in that way, we know what algebra to do.
Yeah.
Where do you suggest we start?
Given that f of x value of k. Okay, well, if we differentiate x over x squared plus 2,
yeah,
then we can find the largest possible value of k is where k is where it equals 0. The largest point. Because that's where it will go from being positive to negative.
Yes, well done. Yes, you got ahead of me there while I was fussing around here. Took my eye off the ball, and you're going with it. Great, yes. Get the gradient function, and we want to find that point that I drew at the top there, because that's how far along we could possibly be. That would be the largest value of k before it starts decreasing again. You've totally got it. Good, good. Right, so if f of x is this is what was distracting me, just getting this stuff to behave. Oh damn. Over x squared plus 2, f dashed of x, and you know that's a notation for the derivative. Yeah. Okay, so how shall we pass this in order to differentiate it?
We could say that's x times x squared plus 2 to minus 1.
Absolutely. Where clearly we're dealing with a composite, an inner and outer. So now we're ready to
say, so that'll be 1.
Yeah.
And then x squared.
Yeah. Ah, now, do you remember I was saying with that quotient rule case, how long ago was I saying that? Was that the last lesson? Yeah, yeah. Oh, but I did mention it earlier. Yeah. You know, because you've got a fraction, we're going to treat it as a product. You've seen that. But remember how we ended up wanting a common denominator here?
Yeah.
And what I nearly but didn't quite do at the time was turn 1 over x into x over x squared. So if we basically raise the power on top, so instead of writing just, because what that is basically 1 over that, instead of writing that, let's prepare for the likely common denominator by squaring it on the bottom. And what shall I write on top? So that it still is this one left alone. I'm not tampering with this expression really, I'm just rewriting it in an equivalent form. 1 over x squared plus 2.
2.
I could square the bottom and put what on top?
I don't know, I thought it would just be 1 still.
Well, no, because 1 over just that isn't going to be the same as 1 over the square of that. So in general, if you've got, so 23, pardon me, I mean, bad example. 1 over 5, if I square the bottom, what must I do to the top here?
Square the top, I guess.
So 1 over 5 equals 1 over 25.
Times it by 5.
Fine, yeah.
We'll work out. Yeah.
Remember, squaring top and bottom doesn't leave the fraction unchanged. You need to think of it as multiplying top and bottom. So applying that.
Okay, so it would be x squared plus 2.
Yes. Okay. Then
x plus x.
Plus x, you mean? Yeah.
And then it would be, so we'd have minus 1x squared plus 2 to the
Yes.
To the minus 2 times 2x.
Yes. Excellent. Now let's just simplify.
So then we just have x squared plus 2 over. Oh, okay, well actually we could simplify that straight away, couldn't we?
What, this?
Why have you?
Yes.
Yeah. Why have you?
Could simplify it because I complicated it from something simpler, didn't I?
Yeah.
Why did I do that? Because I knew, because it was a fraction.
Yeah.
Using the product rule to do a fraction. I knew we were going to need a common denominator.
Right. Okay.
So we'll leave that as it is, despite it being unnecessarily complex. Now let's deal with this one. What have we got here?
And then there we've got minus x. Oh God.
I forget, this is a times sign in there, isn't it?
Okay, well, did you write that? So minus x, would you write minus x cubed?
Y cubed?
Because of the x.
Are you involving this?
No, the other x that's on the left.
Yeah. I mean, this stuff here, this bit here, what's a way of
Yeah.
rewriting minus blob to the power of -2?
1 over
Yes.
minus x squared plus 2 to the squared.
Yeah. So absolutely. Something over x squared plus 2 all squared.
Yeah.
So it would be like that much there is just -1 over that, isn't it?
Oh, so could you write 2x squared over that?
Yeah. But it'll be, you mean just 2x
2x
squared or?
minus?
Yeah. We've got a positive times a negative times a positive is a negative.
Yeah, okay. I thought that would be on the bottom row.
Yeah, all right. But what's the difference between 1 divided by -4 and -1 over 4?
There isn't a difference.
They're both -1/4, aren't they?
Mm.
Okay, so now let's simplify.
So now we can say equals x squared plus 2 minus 2x squared
Yeah, exactly.
over x squared plus 2 squared.
And we can simplify again.
We could probably factorize the top.
Maybe.
So we could say minus 2x. Well, I was just thinking to rearrange it. But,
I mean, there's no factor common to all three terms, is there? But so we would need 2 pairs of brackets. But it's
okay, well, yeah.
overkill, isn't it? Because x squared minus 2x squared is
X minus x squared.
minus x squared. So I could write minus x squared plus 2, or more simply,
Well, if you write minus x squared over 2, then you could.
Did I say over 2?
No, plus 2.
Yes, minus x squared plus 2. It's just that it would be simpler to write. Not much, but it's slightly simpler to write.
2 minus x squared.
Yeah, that's all I'm saying. It's hardly, hardly worth making a fuss about, but we do that. 2 minus x squared over.
Well, yeah.
Yeah. I mean, I can understand if you were anxious to cancel top and bottom somehow.
Could you say can you, so in this scenario, could you say like root 2 minus x over x squared plus 2?
Something like that. Yes, I see your point. You could rewrite the top as root 2 plus x times root 2 minus x, but you wouldn't get the cancelling you were hoping for, would you? So you could do it as a difference of 2 squares, if you think of 2 as a square of root 2. Is that where you were thinking?
Yeah, and then you could get rid of the squares.
Oh no. If you had a square up top, but you don't, it's not like that, is it? And even if it was, I beg your pardon, what you could do then is say it's the square of the whole fraction. But remember what we agreed here, we're not allowed to square top and bottom of a fraction without changing the nature of the expression.
Okay.
So we would be looking for a common factor maybe, but there ain't one.
Yeah, well, we could say x squared plus 2. Hold on. Well, we've got x squared plus 2. It's close, isn't it?
Yeah, it is tantalizing, but I'm afraid the opportunities you're sensing there are traps. Really, no. There's no way to simplify that. You could split it into 2 fractions, 2 over this square minus x squared over this square, And then what? I'm not even sure. But it's not going to lead anywhere good. This is our derivative, basically.
Okay.
It's fine. It's cool like that. Right. So that's correct, isn't it? That's all correct. Yeah, good. So and you knew what our goal was here, didn't you?
Yeah, to then set that to 0.
Yeah. So we're setting this fraction to 0.
Mm-hmm.
So shall I bother to say that, or shall I say something simpler?
Well, I mean, I'd say it's equal to 0.
I mean, I wouldn't bother putting the whole fraction equal to 0. I mean, I might sort of like indicate that we're putting the derivative equal to 0, but I wouldn't bother well, I suppose if I was going to say in other words, I would need to say the whole fraction. But if I say this implies or therefore, basically, fraction equal to 0 is always good news because it just means what's simpler. Fact.
That the bottom's equal to 0.
That would be trouble if the bottom were equal to 0. I mean, if the bottom of a fraction is equal to 0, what happens? For example, what's 3 divided by 0?
0, isn't it?
No, it's
3?
not.
Is it an syntax error, isn't it?
Syntax error. In other words, what you're not allowed to say, 3 over 0, 3 over anything over 0 equals infinity, or undefined, or syntax error, meaning the graph is probably going to have a vertical asymptote.
Right, okay. So the top is
never
equal to
quite
0.
reaches. So the top, yes, a fraction equal to 0 does mean, happily, that
2 minus x squared equals 0.
exactly. Whenever you've got fraction equal to 0, and this often happens when you're differentiating for this purpose, trying to find a stationary point, for example. But it's anytime you're setting any fraction to 0, that just means the numerator is 0, and we go from there.
Then we could say minus x squared equals, or x squared equals 2.
X squared equals 2. It's simpler, isn't it? Yes.
And then x equals root plus or minus root 2.
Yeah. Good. So what's the largest possible value of k?
Plus root 2.
Yeah. Okay. So that was what you planned to do, wasn't it?
Yeah.
And now we've drawn the conclusion of that.
Yeah.
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 Because k was the x coordinate, wasn't it, of where that was happening?
Yeah.
Stationary point was happening. Right. Find the exact coordinates of the points of inflection of f of x. Do you recall what that was about?
Inflection points. Yeah. So that was where it goes from.
Did it here?
So you differentiate. Yeah, you differentiate and then differentiate again.
That's right. So the points of inflection are where what happens?
Or where it goes from like one direction to another.
Yes.
Like where
curvature direction of curvature, clockwise or anti-clockwise. Yes. And
it's a bit confusing.
Yeah.
Like sort of what they are.
Except that if you draw a curvy line there, you've got to change from clockwise to anti-clockwise at some point, haven't you?
Mm, yeah. So you see that line you drew above where you've got the dots?
Yeah.
How is that first dot changing from clockwise to anti-clockwise?
Because if you imagine that you're driving a little car along there,
Yeah.
your steering wheel is turned to clockwise, isn't it?
Yeah.
Now it's
Okay.
very slightly clockwise, but now it must be dead center, mustn't it? And now it's turned to the left. You're turning.
Wait, I'm a bit confused. How is our car? In what way is the car driving along the line?
You're a little bug, a tiny
So
enough
you're on top of the line.
on the line.
You're not like a roller coaster.
Oh, I beg it. Yeah, no, not that. Good. Yeah, sorry, I should have made that clear. Um, yes, you're a bug on the paper there. If it's a paper screen, isn't it? Okay, you're a bug on the screen, driving a little
Yeah.
car, literally along the line, and your steering wheel is sharp right now evening out again, and now you're pointing straight ahead, and now
Okay, I
you're
see.
turning your steering wheel to the left again, and now evening it out. Now you're turning right. Now, oh, now you're turning left slightly, but now again another point of inflection I missed because it's also straight there. The points of inflection are a bit more subtle.
Mm,
And then there'll be another point of inflection here. Yes, I didn't put in all the points of inflection really. There, fair enough. Because now it's a bit, but then by the time we get about there, we've got to turn right again. And here we've got to turn left again. And then it might
mm,
be left all the way from there.
good. Okay, now I understand that.
And how do we do that with algebra?
Um,
Calculus.
so differentiate and then differentiate again.
And then,
Then solve for where it equals 0, I'm guessing.
yes, because when it's clockwise and we're heading soon down,
Yeah.
the second derivative is what?
The second,
If the
when it's
curvature is clockwise so that we're turning soon down or our steering wheel is turned to the right,
mm,
what can we say?
negative,
What do we know about our second derivative?
be positive.
You might think so. Why did I think you might think so? Because you reached a local maximum. But actually, the second derivative, my mnemonic is to think, oh, well, we're heading soon down. So I'll remember that the second derivative is negative.
Right, okay.
Whereas if we've just passed through, or will be, or are passing through a minimum, we're heading soon
Mm,
up, and the second derivative correspondingly is positive.
right, okay.
At the point of inflection is where we're neither positive nor negative.
Okay.
Okay, so what next here?
Then we've got, so we had 2 minus x squared,
Yep.
and then we'll differentiate that.
Sadly, now we do need to use the whole
Okay.
fraction. Yeah.
All right.
We just took the numerator because we'd set it to 0 to find out what value of x it must be. But now to find f double dashed of x, the second derivative, we can use
Mm,
two dashes there to mean. By the way, the other way is this notation we used. D squared y over dx squared. They both mean the second derivative. But we've got to start here.
yeah.
So we've got some work to do. In fact, I better take this down a bit. And let's remind ourselves of what f dashed of x is.
The derivative.
The derivative, the whole of that fraction, though. is what we've got to differentiate now. So that's a more complicated fraction, and you might expect me to say, in that case, well, you do it the proper way and use the quotient rule. But no, actually, this would be worse with the quotient rule.
Well,
we're better off doing it as a product again.
so we could call it 2 minus x squared times x squared plus 2, so minus
Yes.
2.
We're better off doing that.
So then we get minus 2x and then x squared.
Sorry, yes, quite right. Minus 2x, what am I like? Thanks.
And then x squared plus 2 to the minus 2.
Yeah, but with practice, you'll know what to expect here, which is that we're going to need a common denominator, and because of the way this is going to work,
so that'll be squared over 1.
Well, it was squared. I mean, under 1. Yeah. I mean, that's what that is. At the moment, we've written exactly what we should have written. But because we nearly used the quotient rule, we know that we're going to have one higher power on the bottom. So what shall I put on top? I mean, 1 over x squared equals what over x cubed?
I'm not sure.
I mean, bear in mind, x cubed is xxx.
Oh yeah, of course. 1. So x.
So x. 3. So that one of those cancels.
Yeah.
So x. So here?
X.
X.
Yeah.
Oh no, you've lost me.
No, I said x. Did you not hear me?
Yeah, but I don't agree with x here.
Oh, wait, let me think. So we had.
You need to see the point of the example here.
No, I don't. Okay, it's
a square into a cube.
Square plus 2.
Yes.
Yeah.
Really. Now we've got exactly what we've got up here, just written. And we know that we've laid the ground so that we can, we'll have a common denominator as needed. In fact, we might be able to go straight from there to there instead of doing that, if we see the structure of it like that.
Okay.
I keep forgetting to save the wider version of this. Canvas size, width, resize, layer, image size. Fine. So sorry, you were saying?
Then it would be 2 minus x squared.
Only after.
What do you do the other one first? Differentiate.
No, I just wanted that. You were taking that for granted.
Okay,
fair enough.
Yeah.
It's a plus there, isn't there?
Yeah. Plus 2 minus x squared.
Yeah.
Times minus 2 x squared plus 2.
Yeah.
Minus 2 times x squared plus 2 to the minus 3.
Yeah. So I could write it as blob over blob cubed, couldn't I?
Yeah.
Because to the power of minus 3 means over blob cubed. And you see, that's why we wanted the common denominator there. So that's why we wrote that. a bit differently to that. Okay, so
Doesn't have to be times minus 2.
it has to be 2 times that. Sorry?
Yeah.
It has to be minus 2 times that, yes.
Yeah.
So say minus 2 times, you were telling me that, I know. Yeah. So we've got that basically, but.
And times 2x.
Yes. So let's simplify straight away and say minus 2 times 2x is minus 4x.
4x, yeah.
Don't have to, you could leave that, but I probably would. There we are.
And then
all of that, minus 2x, yes, good. That, with an adjustment, yeah. Minus 2 times that, times 2x, yeah. Right, and now, realizing that we've got one big fraction here because of the common denominator, what's on top of the fraction?
it is minus 2x cubed.
Good.
Minus 4x.
Good.
Plus.
Yeah.
Plus.
We could put plus and then put a positive. What would be the positive term?
Minus 8x. Well, yeah, it's plus minus.
And the positive term that we might as well put first would be?
4x squared. 4x cubed.
4x cubed even, yeah, good. Minus 8x, as you said. Super.
Over x squared plus 2 cubed.
Which is going to be equal to?
Which is equal to 4x cubed minus 2x cubed. Oh, there's 2x cubed. Right, 2x cubed.
2x cubed.
Minus 12x.
Minus total 12x, yeah, good.
Oh, you wrote plus.
I did, didn't I? Cheers. Right. Over. And we could take an x out, or we could take 2x out on top, by the way. But that'll do. What next in the larger scheme?
Set it equal to 0.
Yes, good, because we're looking for the
points rate equals 0. So we know, so we could say 2x cubed minus 12x equals 0.
Yeah, that's right. So it's important to see that. And maybe what would you do next actually? Wow, 12x, wasn't it? What would you do next? If you're solving that, how would we solve that cubic?
Probably take x out.
Yeah. Or even
take 2x out.
Probably, yeah.
And then x squared minus 6.
Yeah. Is what's equal to 0, in which case?
In which case, can't you say that's 2x equals 0?
You can say either 2x equals 0, in which
or
x equals 0,
or x squared plus 6 minus 6 equals 0.
Yeah, in which case x squared equals?
X squared equals 6.
And x equals?
X equals plus or minus root 6.
Yeah. So we've got 3 x values. And the corresponding y values, well, we'll have to go right back to the original function, won't we, to get the corresponding y values. So if x is root 6, we get
Root 6 over.
Let's do root -6. Let's do the x values in from left to right.
Okay.
Minus root 6 for an x value. What's the y value?
Minus root 6 over minus 4.
You're plugging minus root 6 into here, yeah?
Yeah.
So you've got minus root 6 on top.
Yeah.
And what have we got on the bottom?
Minus root 6 squared plus 2.
Right. Of course, minus root 6 squared is slightly ambiguous. Do you mean minus the root of or minus the square of root 6 or minus the root of 6 squared, or but we don't, do we? What do we mean?
It means minus root 6 all squared.
All squared, good, which is?
Which is 6.
Yeah. So on the bottom we've got?
8.
Right. So we've got minus root 6 on top, which is root 2, root 3. I'm just seeing whether we can get any better than we can't, can we? So it's minus root 6 over 8 would be our y value. Sorry?
Yeah. Yeah, I'm agreeing with you.
Okay. And when x is 0?
It will be equal to 0.
And when x is root 6?
It will be root 6 over 8.
Yeah. Right. And there's that. Pretty typical application. Really good.
Good.
Right. So it's tough, some of this, but you know, we're seeing how the product rule and the chain rule are all we need in various combinations. You know, you've got the one embedded in the other typically if you're differentiating a fraction.
Okay.
Right. The function f this time is defined by positive real values of x. In other words, it's only defined, if you were drawing the graph of f, it's only going to appear over here. Nothing over here.
Right, okay. Yeah.
It's only defined for positive real values.
Right.
And it's 12 log x. So that explains why it's only defined for positive real values, because as you may or may not be aware, the graph of log looks roughly like that. If that's the y-axis, the graph of log never reaches the y-axis. I won't bother drawing it. Right. Find a set of values of x for which the function is an increasing function.
So we find where the gradient is positive.
Good. Yeah. Right. So if f of x is 12 log x plus x to the 3/2, what's the gradient function, f dashed of x?
Okay, so we would take blob as x.
I mean, we could do. We you know, and then so log of blob would become what function of blob?
1 over.
Yeah. But then we'd say, okay, but we did it with blob. It's the chain rule. Therefore,
12
we've got to multiply by the derivative of the inner function is
1.
only 1. So it's an unnecessary application of the chain rule, isn't it?
Mm.
So we won't bother making a blob here. I mean, there's also no point in making that the blob, because the derivative of 12 of anything with respect to blob is, I mean, the derivative of 12x is
12.
so the derivative of 12 blob in general is
12 blob.
oh, but then that would have been 12x. So I don't know why you're saying 12 blob.
What am I meant to say? Blob. I don't know.
I mean, here we're differentiating 12x with respect to x,
Yeah.
and we say the result is 12.
Yeah.
But that goes for 12 of anything, doesn't it, with respect to that same thing?
Yeah.
So the derivative of 12 blob with respect to blob must be
12.
just 12.
Okay.
That's what we're doing with the chain rule, remember? We're differentiating with respect to the whole of the inner function as though that function were just a variable, with respect to that variable.
Okay.
But then in that case, this 12 blob becomes 12, but then if we're using the chain rule, we must now multiply by the derivative of the inner function.
Okay.
But now we need the derivative of log x. So we still, we might as
Well, when
well.
you get 12 over x.
It's 1 over x, isn't it? But
Yeah.
because it's, basically we skip that. I suppose it is an application of the chain rule when we say that differentiating or integrating any multiple of a function, the multiple just comes along for the ride. You bring it down and you say, okay, that's going to be 12 of whatever this. In other words, the derivative of 12y is going to be 12 times the derivative of y.
Mm.
And so here, what do we get?
12 over x.
Yes, simplified. Good. Nice.
And then plus.
Yeah. Notice
x.
whenever it's plus or minus, whenever you've got differentiating or integrating one thing plus or minus another, you can do them separately and there's no complications.
Yeah.
And this is just?
It would be 3 over 2x to the let me think, to the half.
To the half. Yeah. Exactly. Good.
Good.
So find the set of values for which the function is increasing. You told me exactly our plan. Remind me our plan.
Find where it's equal to anything larger than 0.
Yeah, that's right. We're finding out where this is positive.
Yeah. Okay, so we could say we could multiply through by something.
Yeah. I mean, absolutely. What was? Yeah. Yes. Go on. Go ahead.
12 to.
What should we multiply through by?
What about like over 2? We could multiply through by 2.
Well, sure. Okay, what would we have there?
We get 24 over x plus 3x to the half.
What else could we do?
We could say,
What else could we multiply through by?
I don't know. Is there like a good
Well,
number to multiply
isn't
through?
there another option just as obvious as 2?
3.
But then what was the point of multiplying through by 2? Wasn't it to get rid of a fraction?
Yeah.
Well, can't we get rid of this fraction?
Well, multiply through by x.
Yeah.
I guess. Yeah. Okay. So 24.
Yeah.
Plus. You could say. Just. That would be. Well. 3x to the half times x.
Sure. How would that pan out?
Well, you've got 3 root x times x.
Yeah.
So it's just 3x, isn't it?
Well, what about 3 root x root x?
Well, that would give you that will give you x.
Did you say just 3, by the way?
No, I said
3x.
3x. Yeah.
3x, yeah. Yeah, that's what I thought. Well, that's what gives you 3x. What does this give you? This one is 3x to the half times x to the
1.
1. Why was this 3 times x to the power of 1?
Because you add the powers.
Yeah.
So it's 3x to the 3 over 2.
Yeah.
Then you could say 3x to the 3 over 2 equals minus 24, or not equals, is larger than minus 24.
Yeah. And notice, because because there are no negative values of x, we are allowed to multiply and divide by x on both sides of an inequality with no fear and loathing.
Did you mean to put minus 3 over 2?
No, sorry. Confused by the negatives, wasn't I? Thank you. Here, we're not multiplying or dividing anyway. We're just subtracting 24.
Then x to the 3 over 2 is larger than minus 24 over 3.
In other words, minus
8.
Good.
Okay,
so
And then you could say, so squared. So that means you've got, that's the same as having like 3. Well, let me think. Isn't, so would that be the same as having like 3 over x? Hold on.
You could rewrite it as x to the half cubed.
So then you get a cube root of 8.
Yeah.
Which would
X
be
to the half would be
minus 2.
good.
And then you get square root of minus 2, root minus 2, plus or minus root 2.
But didn't you do the cubed root of this cube? Since you had a cube here, you said I'll take the cube root of each side, quite rightly.
Oh, square it, yeah, of course.
Squaring each side, we get.
You get 4.
Good. Where did we end up doing? The set of values, yes. So the set of values is x values which are
Larger than 4.
larger than 4. So east of 4 on the x-axis.
Yeah.
You know what I mean by east, don't you? I mean, if
Yeah,
that's 4. So these are this is the set of x values.
Yeah.
Well, leave that there. Right. Find the coordinates of the point of inflection now of the function.
Okay, so where did we get to with differentiating it? Once we differentiated it.
That's right. We had the original function, f. F dashed is the gradient function, the first derivative.
Okay, so we differentiate that then.
Yes.
But can't we take the simpler form?
Yeah, we got, no. We only simplified the statement that the gradient function had to be greater than 0. The gradient function itself, you know, where would we stop? Here, here, here. This was all about balancing. So no, we do have to go back to here.
Okay.
So let's do that. 12 over x plus 3 halves x to the half is f dashed of x. So f double dashed, okay? You're familiar with the what we're talking about, yeah? So?
Okay, so then you'd get, so 12 over x is the same as 12 times x to the minus 1.
Good.
So 12x to the minus 1, you could say minus 12x to the minus 2.
Absolutely. We can put as minus 12 over x squared, but you haven't got rid of both the x's, so let's not bother. Yeah.
Yeah, plus 3/4 x to the minus half.
Which you could rewrite as over root x. Good. But that's fine like that. And the coordinates of the point of inflection they wanted.
So where it equals 0.
Yeah. So putting that equal to 0, shall we do the same thing again, multiply through? That was a good idea. I mean, it was a good idea when you said it, and then you seemed to
I just wasn't sure if you could multiply through by x. Like I didn't know if that would make sense.
Yeah,
I
I
did
mean,
think
2
you
wasn't
could.
so profitable anyway. It was the x that
Yeah.
did the, you know, had the benefit really.
Okay. Well, multiply through by uh, 4,
4, but also
but also um, I don't know, -1.
I mean, what's the other way of writing minus 12x to the minus 2? Let's rewrite it that way first.
Okay. -12 over
Yes.
x squared
Yeah.
plus 3 over 4 over.
I mean, in a way, it's 3 over 4 root x would be 1, but I'm not so worried about that. I would write. It, it might be easier to think of. It will be easier to leave that as it is, I think,
Okay.
when we do what we're going to do next.
So then multiply through by x squared.
Yes. But let's go with the 4 as well. Let's multiply through by 4x squared.
Okay. So then we've got okay, so then we've got minus 48
Yes.
plus 3
Yeah.
x to the, so multiplying those, wouldn't you say to the 1.5?
Yes. But I would say 3 over 2. But yeah.
Equals 0.
Good. And now?
And we can say 3x 3 over to the power 3 over 2 equals 48.
Keep going.
And then x to the 3 over 2 equals 16.
Yeah.
And then x to the half equals cube root of 16.
Yeah, that's true. This seems weird, these numbers, but perhaps they're correct. And by the way, yes, you want to take the cubed root. The easiest way to do this stage,
Yeah.
we did it in 2 parts before. We said, look, let's break it apart and do them separately. But in general, if you're trying to make x the subject here, you just want to reverse that by raising each side to the power of, power of 2/3. It was what we were doing there. I'll take those away there, but because it'll muck it up. But this means that what we've got here is x to the 2/3, which is horrible. Cubed root of 16 isn't a thing, is it? It's not a nice integer.
Yeah,
16
no.
squared is a thing. We could say what we've got is the cubed root of 256, or 256 to the power of a third. But I'm a bit surprised by that. So the coordinates are, and it's only 1 point because they told us, so we won't worry about the signs here. But the x value is,
the x value is
256 to the power of a third, and the y value then?
we've put it into that equation.
Yeah. So that would be horrible in there, won't it? 12 log of the x value plus x to the 3 halves. At least x to the 3 halves is nice. It's 16, isn't it?
Yeah.
So that bit is okay, the plus x to the 3 halves. But the 12 log of that, I wonder if it simplifies. Let's have a look at that. 12 log of 16 to the power of 2/3. Now, what was this log rule we were talking about yesterday? Log a to the power of b. How can we rewrite that?
B minus b log a. Or b log a.
Just b log a.
Okay.
I mean, if it was minus b, if the power were minus b,
Then it would be
but that's
minus
another
b.
reason, by the way, yes. The fact that log a to the minus b would be minus b log a explains why minus a log is 1/, because, you know, that means reciprocal there, you can see.
Yeah.
A to the minus b would be (1/a to the b).
Right. Okay.
Anyway, so this does, if we apply that here, it's nice, isn't it? If we apply that to this, what do we get?
We get 8 ln 16.
Yes. And given that that's the same as 8 ln of 2 to the power of
4.
We could now rewrite that as how many log 2?
32.
So that would be the preferred presentation. Oh, I didn't have room for it. 32 log 2 plus 16. Bit squashed there. Whew. Right.
Good. They were good questions.
Right. Well, yeah, they're more good examples of product rule. Oh, that one wasn't product rule or chain rule, was it? Good. It was just more of the theory of differentiation and why we're using it, but which is why. But it's more. Notice you've got a combination of ordinary power rule or polynomial stuff, and you know these other ones, the log, sine and cos, and then all of those are all of what you need along with the chain rule and product rule. And right.